So let's take a look at the first part of our EMI filter. As you can see, first of all, we have two inputs. We have an AC input in case you want to input unrectified AC voltage with a simple full wave bridge rectifier. And this is the output of this goes to the normal, let's call it DC input. And the first component we have is a special feed-through capacitor. This has only 10 nanofarads, and this is a special very high frequency capacitor which really can filter out very high frequency noise above the 30 megahertz that we basically want our filter to be designed for. It has these are two very small ferrite beads integrated into this. It's even called an EMI filter, but of course it's not a complete filter. It just has some very low inductivity ferrite beads and this feed-through capacitor. This really only serves to keep out very high frequency noise in the range 100 megahertz and above. We have this just for to make it safe. We have the same filter behind the common mode choke, and here you can see the common mode choke, which consists of technically of two windings. The little point here indicates the start of the winding, and that way the direction of the winding. So this is our basic component to filter out the common mode noise, a common mode choke, or sometimes also called current-compensated choke. So except for these two additional elements, this is the basic element for this nasty kind of noise, which there is basically no other way to filter this out except with a common mode choke. So now let's take a look at the filter elements behind or after the common mode choke. As you can see, it are always combinations of inductivities, in this case two in series. The one that I've crossed out is simply a second one for the 5 amps version. So in fact there is either this one or this one. We have here two inductivities in series with different values, and here we have 6 capacitors going from 100 microfarads down to 1 nanofarad, all in parallel. We'll later explain first of all why inductivities and how they work, and why we put at least 2 in series, and how capacitors work to filter out differential mode noise, and why we put in this case even 6 in series. Now this little resistor here of 100K, it just serves to discharge the big main capacitor, simply because we also have a 400 volt version, and the high voltage electrolytic capacitors, they can keep their charge for extended periods, even days, weeks or months. And if you have no load connected, then they will be fully charged up, and the voltages 100 or even 400 volts are already quite dangerous. So this simply discharges the main capacitor in case there's no load connected. And then from here it goes directly to the what's called plus out. That's the main DC path, and we have a second path which is here called, the output is called Anode. That's simply for further suppressing noise in the low hertz region, and this can only be accomplished by an RC filter. First of all a resistor, and then a very heavy, very big capacitor of 1000 microfarads. And we will later see why this is necessary, that we need an RC combination. And again, 6 capacitors in parallel going from 1000 microfarads again down to 1 nanofarad. So the basic filter is this: 2 inductors and then 6 capacitors in parallel. We have an additional anode voltage RC filter behind this for additionally filtered anode voltages of tube amplifiers. And then finally you can see we not only have the circuit ground out connection, but we also have an earth connection. And there are again a combination of 2 capacitors in parallel. The first one is between 100 nano and 1 microfarad, and in parallel there is a 1 nanofarad, and it goes from earth to the positive output and to the ground output. And ground output is not equal to ground input because we have a separate ground due to the common mode choke, which sits between the input ground and the output ground. So that is quite important, that there are 2 grounds, input and output, and the earth again is separate. Just to tell you, it's not always advisable to connect this earth really to your local earth. You have to try it out if the noise becomes lower, but it also can become higher. That depends on your local situation of the potential between your earth and your circuit, how many noise there is generated. So you can either improve the situation by connecting this terminal with your local earth, but you can also make it worse. So really you have to try it out. So that are the basic elements. We only have some inductors in series, some capacitors in parallel, a discharging resistor, an RC combination for additional filtering for the anode output, and some special capacitors. They are called X2 capacitors, which filter out earth generated noise, but as I already told you, try it out if it improves your situation or makes it worse. And now finally we have to explain why do we need 2 inductors in series on the positive and on the ground side, and why we have 6 capacitors in parallel as well on the mains output or main output, DC output, and on the separate anode voltage output. So just to explain why we have to put many capacitors in parallel and inductivities in series to get a good suppression of noise, let's start with the more common known element, the capacitor. Let's presume we have only one capacitor going to ground, and here we have the first of all our DC voltage input, and of course we have our load. And to get some significant figures, let's suppose an average example where we have a 12 volt DC input and a load of 12 ohms, which gives you 1 amp of DC current here. Now, as you might know, for DC a capacitor has infinite resistance, so the total current is flowing through the load. But we know that our noise is not DC, but it's AC. And the properties of a capacitor is that the higher the frequency, the lower the what we call AC resistance, or in technical terms the impedance of the capacitor gets. Now just to give you an impression how this looks like, let's make a diagram where we have the frequency on the x-axis and the impedance of the capacitor, which you can imagine as the AC resistance on the y-axis, on the vertical axis. Now, if we know that for DC current, the frequency is 0, and the resistance, the AC resistance, the impedance of the capacitor is infinite. So the graph would start here outside the diagram, and if we have a linear scaled x-axis, the impedance would look like around this, and the formula is the impedance of the capacitor is 1 on 2 pi times the frequency times the capacitance, and basically that's a 1 over c, and this gives a hyperbola. So, but this is not very convenient for real calculations. So let's redraw our figure how the impedance changes with the frequency for a range of what is of interest for us of, let's say, from 100 Hertz, where we know that our hum from the line voltage comes from, up to, let's say, 100 megahertz. And if the scale of the x-axis of the horizontal axis, where we put our frequency, if it is logarithmic, then it means that every tick that I draw now is a factor of 10 upwards in frequency. So the next tick would be 1 kilohertz, 10 kilohertz, 100 kilohertz, 1 megahertz. Of course, it's not very good. The divisions are not constant, but let it suffice for now, and 10 megahertz. And now we make the vertical axis, the x-axis, where we show the impedance of the capacitor. Let's also make it logarithmic, and the range of interest for us is between 10 ohms and, let's say, 1 milliohm. So again, each tick is a factor of 10, and it goes down to 0.01 ohms, which is 10 milliohms, and here we would have 1 milliohm. And now the impedance of the capacitor would look like this. Now it's a straight line if we would have an ideal capacitor. So if we go back to our real circuit, what does this mean? Now, if we know that a capacitor, that the impedance, the AC resistance, drops with frequency, that means that we have to find a capacitor that simply shorts out any undesired noise, any undesired frequencies. And our aim is that from 100 Hertz up to 30 megahertz, the impedance should be smaller than 1 ohms. Why? Let's suppose this would be, we draw this as a resistance, and now if we have a load of 12 ohms and here a resistance of 1 ohms, an impedance of 1 ohms, but which we also can treat as a resistance, then we know that most of the current, if it's below 1 ohms, will flow through here, through the capacitor, and not through the load. So that's the effect of a capacitor going to ground. It simply shorts out any frequencies. Now we still have to find the right value, and we have to see if one capacitor is really enough to short out all frequencies from 100 Hertz up to 30 megahertz with an impedance smaller than 1 ohm. And therefore we just take a look at a real capacitor. So now here we have the real impedance of real capacitors, and there's a bit of a surprise. Remember that the ideal curve would look like this, and what's here designed as aluminium electrolytics, they start with this linear fall of the impedance with frequency, but then they have a minimum and then they start to rise again. First of all, we can take a look which size of capacitors do we need to get here at 100 Hertz to get an impedance of below 1 ohms, and that would be something, an electrolytic that would be greater than 1000 microfarad. We would probably need more than 10,000 microfarads to be in the range of 0.1 ohms. And well, that's not possible with our filters simply because of size. We want our filter to be also working with high voltages. We have it in 3 different shapes for 50 volt, 100 volts and 400 volts. Here is the 400 volt version, and the biggest we could get in which is not too big, is 100 microfarad. So if you look at the curve of a 100 microfarad aluminium electrolytic capacitor, then we see that at 100 Hertz the impedance is around 20 ohms. So this is not sufficient to suppress 100 or 120 Hertz hum, simply because of the value of available aluminium electrolytics for high voltage. It's just not enough, but we'll deal with that later, how we suppress 100 or 120 Hertz hum. So the useful range where it falls below 1 ohms is, let's say, about, this is 1 kilohertz, let's say from 2 kilohertz, and then it goes to a minimum, and at around 10 to the 5th power, which is 100 kilohertz, it starts to rise again. So it's useful only the 100 microfarad aluminium electrolytic. This type would be usable up to around 100 kilohertz. And now we'll explain just in a minute where this behavior comes from and why the impedance starts even to rise again after the minimum here. But you already can see, if we take higher value, not in this case not aluminium electrolytics, but if we take ceramic capacitors, they go down much more to a much lower impedance, and they have a much better behavior. So these are multi-layer ceramic capacitors, but there's a problem. It would be nice to get one with 10 microfarads and 50, 100 or even 400 volts voltage range, but they are on in this 1 microfarad or even 10 microfarad. They are available only for up to 16 or 25 volts, so they are of no use for us. But the same behavior as these multi-layer ceramic capacitors are good film capacitors, and these are available for high voltages. No problem to get one with 1 or even 10 microfarad, which can withstand even 400 volts. And now comes the trick. If we take for the lower frequency range, let's say the useful range where they are around 0.1 ohms impedance from 1 kilohertz up to 100 kilohertz, there the a 1000 microfarad, or if we get a little bit lower, 100 microfarad is useful. And then we parallel, first of all, a 10 microfarad film capacitor, which simply takes over. If it's in parallel, then the aluminium electrolytic will have no effect here from this around this frequency on. But now the film capacitor takes over, but only to around 300 or 400 kilohertz. Then it starts to rise again. When we say the limit is 0.1 ohms, then the useful range would be up to 20 megahertz. And then we just parallel either 1 or 2 more. A 1 microfarad would already go up to around 20, no, up to, this is already 10 megahertz, up to 20 megahertz. And if we will then still take a 100 nanofarad film capacitor in parallel, this would be have a sufficiently low impedance up to 100 megahertz. So you can imagine this as, when we parallel these, we would get a resulting curve that would look around this way. First we have our, we'll draw again. Here we have 100 hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz, and finally 100 megahertz. Now we start with our 100 microfarad capacitor, which is only useful around up to here. Then the 10 microfarad film capacitor takes over. Then our 1 microfarad film capacitor takes over, and when it starts to rise again, the 100 nanofarad will take over, and we get around this impedance curve. And when we say this is our 0.1, here is the impedance, here is our limit, our 0.1 ohms resistance, then this combination would be useful from around 30 kilohertz up to 100 megahertz. And if we lower, well, if we say even 1 ohm would give a good suppression of noise, then the range is even a little bit further. It would be between, let's say, 3 kilohertz to around 300 megahertz. So that's the trick, simply by paralleling a the biggest available aluminium electrolytic together with either ceramic or high quality film capacitors, you get the, and only by that way, you can get the impedance constantly over a broad frequency range below 1 ohms or 0.1 ohms. This is around the limit here. Other factors like the ohmic resistance of your PCB traces, etc., will come into play. So now that's the explanation why we put many capacitors in parallel. We will, in the next and final episode of this video series, we will demonstrate this with a spectrum analyzer. If we put first only the aluminum electrolytic into the circuit, and then we add one capacitor after another and compare the resulting impedance curve. Now, what is missing is still an explanation why any capacitor tapers off, has a minimum, and then starts to rise again. Well, first of all, why there's a minimum at all is simply you also have an ohmic resistance simply of the leads to the capacitor, and furthermore, any capacitor, you know, there is nothing like an ideal component. A real capacitor looks like this one. You first of all have the ohmic resistance of the leads and internal ohmic resistances. Then you have the capacitor itself, but you also have inductance in the leads. So you have finally a kind of series, that is exactly what a series resonant circuit looks like. That's the combination of a resistor, a capacitor, and an inductance put in series, and the inductance, that is the component that makes the impedance start to rise again, because it has exactly the opposite behavior than the capacitor. And the resistance, the parasitic resistance, that is the reason why we have an absolute minimum, which, as you can see with multi-layer ceramic capacitors, is much lower, as well as with good quality or high quality film capacitors, is much lower than with a standard aluminium electrolytic capacitor. So in this very informative graphic or diagram, we see how it all works together. We have first of all the impedance straight line from the basic capacitor. Then we have here the so-called equivalent series resistance, which are the ohmic losses, the resistive losses in the capacitor. And this would be the green line here. This is the parasitic impedance of the capacitor, which when we would be able to look at it alone would be a straight line going up. And when we add all three together, we get exactly this behavior, that the impedance of the real capacitor falls off up to a minimum, which is caused by the equivalent series resistance, and then it starts to rise again due to the parasitic inductor. So that is typical for every real-world capacitor and Now you know where this behavior comes from and what you have to watch out for when using real-world capacitors to suppress any noise or to filter out anything or to get a minimum impedance that you want to desire for a larger frequency range. So it's the parasitic elements inside any real capacitor that give this curve, and you see you cannot filter out or you cannot short out in our case, because remember the purpose of the capacitor is to short out high frequency noise down to ground and let the DC path to our load is there is no effect. It only shorts out AC voltages. And well, finally, or the final result is we have to put 2, 3 or more high quality ceramic or film capacitors in parallel to keep the impedance over a wide frequency range below 1 or 0.1 ohms. So that was the explanation why we parallel capacitors, and now let's take a look at our inductance, why there we have to put at least 2 in series to get a good suppression or absorption of radio frequency noise. So with capacitors we had the purpose that the capacitor shall short out any high frequency noise down to ground. Now let's take a look at how this looks like for an inductor that we put in series. Now we again have our DC source plus noise, let's call it that way, and now we put an inductor in series to our path to our load, and we again assume we would have a 12 ohms load where 1 amps of DC current is flowing through, and we have a 12 volt DC power supply. And now you only have to know inductors always behave the exact opposite to capacitors. That means that the impedance, the resistance to AC voltages simply rises linearly, and this time no matter if we put linear axis or logarithmic axis, the impedance, we call it XXL of an inductor, rises linearly with frequency, and the correct relation is that the impedance is simply 2 pi times the frequency times the inductance. That's why it's absolutely linear. And just as we saw with capacitors, where we also could say the bigger the better, because remember, a bigger capacitor has at the same frequency, at least in the range where the ohmic parasitic resistance and the parasitic inductance doesn't play any role. The bigger the capacity is, the lower the impedance is at the same frequency. That's why we can call it the bigger the better. And the same is true with inductance. So we can look upon this as a voltage divider if we draw it a little bit different. Here we have the inductance, and here we have our load, and again ground, and here our DC plus noise source. Now for the pure DC current, the impedance of the inductance is ideally zero. Of course, it's not in reality zero. It remains the ohmic copper resistance of the coil the inductance is made of. But if this is, let's say, below 100 milliohms, then a load at a load of 12 ohms, there is nearly no voltage falling off at the inductance, but all the voltage is present here at the load, because we would have a relation of, let's say, 1 to 100, which means the load is 100 times greater, and that means that more than 99% of the voltage is present, and less than 1% of the voltage is here at the inductance. But as the frequency rises now, the impedance, the AC resistance, remember, we also always can see or look upon the impedance as the resistance to an AC voltage. Now, the higher the frequency becomes, the more the impedance, the AC resistance of the inductor will rise. And when it is 12 ohms, we would have a voltage divider of 1 to 1, which means only half of the, in this case, noise frequency will be present at the load, and the other half is absorbed here. And to get a good suppression, we have to look for at least a factor of 10 to 1, which means that the impedance at the inductance is 10 times greater than a typical load, which in our case would mean that the let's call it this way, that the impedance of the inductor shall be greater than, let's say, 100 ohms. Now, this is what we are seeking for, an inductor which for all frequencies from, let's say again, 100 Hertz up to 30 megahertz is greater than 100 ohms. And of course we could calculate which inductance do we need to meet this criterion, but let's directly take a look at a real capacitor, how the impedance curve of a real inductor does look like. So here I've taken the data sheet of a real RFI suppression inductor type, and surprise, surprise, we see that we again, just as with capacitors, we see first of all a textbook linear rise, but then we get a maximum, and then the impedance falls again. And we said we want something that is, here the y-axis is in kilo ohms, so we need something, we need an impedance greater than 100 ohms, which is 0.1 kilo ohms. And we search for, here you also can see the bigger the better. A higher inductance gives you the same impedance at already a lower frequency. So let's compare this. A 10,000 microhenries, which is 10 millihenries, inductor will give you already 1 kilo ohm of impedance at, what's this, 0.02 megahertz, which is 20 kilohertz. A 1000 microhenry inductor will give you at the same frequency only an impedance of 0.1 kilo ohm, which is our desired 100 ohms. And if we again take a smaller inductance of only 100 microhenry, then we get an impedance of only 10 ohms at a frequency of 20 kilohertz. So the bigger inductor gives us a better absorption or suppression of even in the low frequency range, but there's a catch. These are already so-called high current suppression coils. Now we have a second demand to our inductor, and that is it has to carry, at least depending on the type of suppression filter we have, it has to carry at least 2 amps, or in the high current version 5 amps. And now let's see, this is the maximum current they can carry before the ferrite core gets into saturation. And if we make a mark here at around 2 amps max current, then we get at 100 microhenries. And that's exactly the first inductor. We choose a 100 microhenry, 2 amps rated inductor. And now let's go back to the impedance curve. Now this is the 100 microhenry typical impedance curve. And let's remember again, we want to have a impedance of 100 ohms or 0.1 kilo ohms or greater. And this is only reached for frequencies around, let's say, 0.2 megahertz, which is 200 kilohertz up to around 3 megahertz. So what we need is with one power inductor for RFI suppression is only we only get this from 200 kilohertz up to 2 or 3 megahertz, and then there's a peak reached, and then the impedance falls off again. And if we would draw the curve further to the right, it would fall below 100 ohms again in the 20 or 30 megahertz range. And again, if we now parallel a second inductor to the first, then the second inductor will just take over when the impedance of the first coil starts to fall below our desired value. That's the reason, basically the same reason as with our paralleling of capacitors, that we take at least one second inductor in series. When this inductor falls off in impedance, then the second one with a lower impedance, with a lower inductance, has due to beta values at higher frequency, this takes over. It doesn't make sense to to put a third inductor in series. Remember, we only need a suppression up to 30 megahertz. So a 100 microhenry and a 10 microhenry inductor will be sufficient. We can't get bigger than 100 microhenry simply because we cannot get an inductor which can carry 2 or 5 amps max current to be bigger than 100 microhenry. Otherwise, the inductor would become impractically large. So that's the reason why we only have 2 inductors and not 3 or more, as in the capacitors, where we have, at least for a first try, we have 6 capacitors in parallel. We can't get higher than 100 microhenry, and the 10 microhenry inductor is sufficient to get a sufficiently high impedance up to 30 megahertz. Now, there's a last question concerning the inductors. Why is this fall off here, and why is this maximum here? And the reason is basically the same as with the capacitors. It are the parasitic elements. Every inductor has, due to the capacitance of one winding to the next, has a parasitic capacitor in parallel. And of course there is still the ohmic resistance, depends on the real building of the inductor. If you draw it here to the right or here before the parallel capacitor, it would be probably more exact to draw it this way. So we have the basic inductance and the parasitic ohmic copper resistance and the parasitic capacitor, which is usually formed by the capacitance from one winding to the next. And this looks suspiciously like a parallel resonant circuit, and it's exactly what it is, because this curve is the curve of a parallel resonant circuit. And the peak would even go up to infinity. It would be the impedance would be infinitely high if we wouldn't have a parasitic ohmic resistance due to the copper resistance and other effects which also give you, like the so-called skin effect, which we'll explain in in another video series about AM antennas. So let us suffice to say we have again parasitic elements which make the inductor non-ideal. An ideal inductor would have a straight line going all the way to the right, and it would have no maximum and no fall off after the maximum. So now we have explained 90% of our real filter. I'll show you once again here the first special capacitors with which also have these, it's better seen here at this type, which has here the ferrite beads on the input and the output. And you also can see here they are not ideal. We choose the 10,000 picofarad, which is 10 nanofarads. You see that you have the same behavior, though it's a little bit sharper than here. But you have basically the same behavior, because even this high frequency RFI suppression type capacitor is not ideal, nor are the ferrite beads ideal, but it's better than a standard capacitor to suppress very high frequency noise. So this, in the beginning, they are only for suppression or absorption of very high frequency noise above 30 megahertz. We have our common mode choke or current compensated choke. We have, as the next stage, 2 inductors in parallel, and the next stage are the 6 paralleled capacitors from 100 microfarad down to 1 nanofarad. We have a discharge resistor, which is here in the 400 volt version. It's separated into 2 single ones, simply because they are only rated for 250 volt DC, so we have to split one capacitor into two, the same as here, where all resistors are split into two. And what remains is, why do we need this extra RC combination here for the so-called anode voltage output? Now, we have seen whatever we do, we don't get a good suppression in the 100 hertz hum, in the range between 100 hertz and, let's say, 2 or 3 kilohertz. We simply can't get a large enough inductor or electrolytic capacitor to get it below 1 ohm impedance. So we have to do a trick. And that's what I explain on the next page. So let's take a look at what we in our filter call the anode filter, and that's the final and separate stage for filtering out the lower frequencies, in especially 50, 100, 120 hertz hum. So let's say basically everything below 3 kilohertz. And there is only one way you can do this with passive components, without too much components. And for DC current, let's suggest we take a 100 volt source. And of course, before the RC filter, we have an impedance of our source of nearly 0 ohms, because all the other elements that we're using in our filter have only series resistances in the milliohms range, so we can take this as 0. So we have a very low impedance voltage source in front of the filter. And then you might know that an RC low-pass filter looks like this. We have a resistor, let's take for an example 100 ohms, and we have a capacitor. In this case I did draw an electrolytic capacitor, let's presume 1000 microfarads. Now the first thing you will say, hey Roger, but what about the impedance? We lose the low impedance if we put a 100 ohms resistor in series with our DC current path. Well, yeah, that's true, but let's see how our load looks like. It's called the anode filter because it's designed, or is supposed to be for tube anode voltages. And you might know that a tube, except for many other grids and something like that, especially has an anode and a cathode. The anode is where the positive voltage is supplied, and the cathode, current flows in this direction. Of course, the electrons are going in the other direction, but the technical direction of current is from plus to minus. Now, what is that is our load, in this case one or more tubes. And what is the impedance of our load? Now, you might already know that tubes work with high voltages, in this example here 100 volts, but with very low currents. And that means that the impedance of our load is usually in the kilo ohms range. And because it's so high, that's why we can even use a 100 ohms resistor for filtering out, because if the load is at least 10 times greater in impedance than our series resistor here, it doesn't make there's no big voltage drop. But the bigger this resistor is, the better is the suppression of low frequency noise. So let's stay with this example. Of course, if you have lower impedance loads like heavy power tubes, you can use another resistor like 10 ohms. So the calculation becomes different. Of course, if you have a lower value of this series resistor, then your filter will become less effective at the same frequency. So you should always seek for as in most of our filter elements, the bigger the better. The higher the capacitor here is, the better is the suppression of low frequency noise or hum, and the bigger this resistor is, the better is the filter. So you're usually limited by simply the available size of high voltage, high capacity, high capacitance electrolytics. So that's even a relatively big beast here, a 100 volt, 1000 microfarads electrolytic. And the other thing you are limited is just you take simply the highest resistance that is still feasible with your load impedance. Usually you take a value of 1/10 of the value of your load impedance. So, but now we didn't say anything about what's it really doing, and that's we'll take a look at our next graph. So to understand how such an RC filter works and can suppress low frequency noise, hum, or anything that's in the low frequency range, let's draw the same circuit, or well, circuit is even a bit exaggerated. This part of our filter, again, a little bit different, and then I hope it becomes clear how it works. We have our series resistor R, which in our example is 100 ohms. We have our capacitor, in this case an electrolytic, but that doesn't matter, C, and from here we also have the load going to ground, also with its load resistance or load impedance. Now here at the upper side we have our supply voltage and coming into the filter, and what we want to know is what is the voltage here at the load. What happens with high or low frequency noise? Now you might see this is nothing else but a voltage divider, and it's a frequency dependent voltage divider. Now you might remember from the parts before that the impedance, or let's better call it the AC resistance of a capacitor, goes low when the frequency goes up. That means the higher the frequency, the lower this impedance here from our capacitor becomes. Now, what if we have a voltage divider with a part here that has a much lower impedance than here? Then it does nothing else but simply short out the low frequencies to ground, and nothing remains here for the load. For DC, this is the impedance is infinite. So for DC, and that's what our filter is designed for, to have minimum resistance for DC, then the capacitor simply doesn't exist, and we only have a voltage divider between our series resistor and the load. And if we know that the load is at least 10 times higher than here, the series resistor, we get nearly the full supply voltage here at the load. So that's the reason why we want to have a series resistor at least, or at maximum, 1/10 of the load resistance, because in that case we have only minimal loss of supply voltage here in the resistor. But what happens when we go away from DC and look at what is AC? Well, the AC resistance of pure resistors is the same as the DC resistance, but now the capacitor comes into play. And as I already said, for AC, the capacitor here can behave nearly like a short. And the higher the frequency, the lower the impedance gets. That means any frequencies above a certain, let's call it limiting frequency, will be shorted out to ground and cannot reach the load, or well, they are of course present at the load, but at a much diminished level, because then the voltage divider behaves in a way that nearly all the voltage, all the current here goes to ground through the capacitor. And you don't have to care about the theory behind it, even though it's relatively simple. But there is one important formula, and that's what is called the suppression ratio. That means the ratio between the level of the noise here at the input of the filter and what remains of this noise here at the load level. And this suppression ratio is calculated as 2 pi times the frequency we want to look at times R times C. Now again, we see the bigger the better. We want to have as large suppression ratio as possible, and that means a resistor as large as possible and a capacitor as large as possible. And now let's calculate just for our example of 100 ohms and 1000 microfarad what kind of suppression ratio we get for 100 hertz, and then the formula looks like this: 2 times pi times 100 hertz times 100 ohms times 1000 microfarad. And let's put this into the calculator and see what we get. Shorten it up with pi is 3.14 times 100 times 100 times 1000 microfarad, and this gives us a suppression ratio of 62.8. That means if we choose our resistor as 100 ohms and our capacitor as 1000 microfarad, then 100 hertz, and this is only valid for the frequency we put into the formula. This is only valid for this result, is only valid for 100 hertz, a 100 ohms resistor, and a 1000 microfarad capacitor. Then we get 100 hertz suppressed by a factor of 62.8. Let's round this up to nearly 100. So the 100 hertz hum is suppressed more than 60 times here at the load than it was here when it arrived from the power supply. And I think that's quite substantial, and that's also what we want to get. We want to get around a factor of 100. So in our real filters that we finally built, we in fact did choose a capacitor of 1000 microfarad, or in the case of the 400 volt version for very high voltages, we only could get 820 microfarads, but that's near enough to 1000 microfarads. And we choose 100 ohms as a resistor, but you can solder a second resistor simply in parallel If you want a lower value, let's say you put 11 ohms or 12 ohms in parallel, then this will give you around 10 ohms resulting resistor. If you want to go the other way, you want to get even a higher resistor for still better suppression, and if it doesn't matter to you if it's 1 kilo ohms in that case, then you simply snip away the existing resistor and put your 1 kilo ohms resistor in the parallel place where we left some place free for a second resistor. And you even could, if you want to, put a 0 ohm resistor, is simply a wire bridge here. Then you of course have no filter, no additional suppression of 100 Hertz hum, but you have a bigger capacitor in parallel to the first capacitor on the other half of the filter. So we try to make it relatively universal so that you can play around with it. But there's still one final thing that's also very important to know. What's the wattage that your resistor must have, and you really have to watch out for this. Let's take a clean piece of paper, because you might have seen in one of our other videos that what I call Ohm's law of resistance is the power that is put into heat in a resistor is either the voltage squared divided by the resistor, or the current through the resistor squared times the resistor. Now let's suppose you really use this for tube anode supply, and let's say you have a current of 50 milliamps and a resistor of 100 ohms. So let's see then what the power that is turned into heat in this resistor, how big it is. And we take 50 milliamps times, to square it, and times 100 ohm, and that's already a quarter watt, and you should at least take this into consideration. So that's nearly the limit that a usual metal film resistor can withstand for extended periods. If you raise the current substantially above 50 milliamps, then you have to use a resistor with a higher power wattage. Let's make an example with 400 milliamps. And now we even lower the resistor to 10 ohms, and let's see what this gives us. We get 0.4 amps squared times 10 ohms, and that's already 1.6 watts. So you need at least a 2 watt resistor for withstanding a heat generation of 1.6 watts. So just watch out what your real current is that you are driving through your anode filter. The capacitor only has to withstand the voltage, the maximum voltage you put it at the input, but the resistor, here all the current that flows into your load also flows through your resistor. And so make your calculations before before you turn on power to be on the safe side. So that was the final filter function, how to filter out low frequency noise, especially in the audible region, especially the 100 or 120 hertz hum. We could see the only physically feasible way to do this with components that are not that big but only that big is with a RC filter, with a resistor and a capacitor. And that was the final section of our filter. And now to end this episode, let's take a look at how some real filters look like and compare them with what if we find anything that any stages that we did talk about, if we find them in real commercial filters. So let's start with this kind of integrated filter, which comes with an IEC plug or a socket in this case. And you already can recognize there are some elements, though it's difficult to show it to you so that you get no reflections. You already can see here we have a common mode choke, we have two what's called X and Y capacitors, one of them connected to the earth. And so that's the simplest and smallest of our filters, but remember, the bigger the better. This filter can filter out some of high frequency noise, but it doesn't do it very good. It's better than nothing, but absolutely not sufficient for our purposes. And remember, this is an AC mains filter. Our filter is designed for DC voltages, so that makes a bit of a difference. So next is a much larger filter. I once have built this from a kit to supply the power, or to filter the AC mains power for my home build high-end preamplifier. In the end I didn't use it, that's why it's lying around here, because I switched to rechargeable batteries as power supply, but that's another story. So the current flow is from left to right, mains in is here, and we recognize again some elements. This is the common mode choke. These are the two separate chokes, even they are wound onto one common ferrite core, but these are exactly the two same inductances that we also have in our filter. Of course not the same type, but the same function. We have some capacitors, very small ones, because this filter is for AC mains voltage, not for DC voltage. We have discharging resistors, just as in our filter capacitors, which also must be discharged. And we have two little capacitors going or connected to earth. PE here is the protective earth. And so we recognize some elements that are also used in our filter, and there is something additional. You can put this protective shield over it, and that's the last thing you have to consider, because you not only can get noise over your lines, over the leads, but you also can get noise directly as electromagnetic radiation going into your circuit. And that's why you, in case you have really high frequency noise, you should use such a cover made out of special what we call Weissblech. I will look up the translation for this. This is a special kind of sheet metal that can be easily soldered. So it's covered with either with tin or with zinc. I don't know exactly. Anyway, what's the reason for this? We can see this in this little graphic here. Sorry again that it's in German, but I will explain it to you. Here we have the frequency. Here we have the percentage that comes either of the noise coupling into your circuits, either through the leads or PCB traces or wires, and the other half is the percentage that couples into your circuit via electromagnetic radiation, which can be shielded with such a metal tint metal cover. And we see that around a frequency in the range between 1 and 10 megahertz, that's the region where the radiation coupling takes over. So if you really have relatively high frequency noise coming over the air, so to speak, then you should use such a tin-plated metal cover. And so what do you think what we put also into the filters we finally designed? These are the final prototypes of our filters. I'll show you 3 examples. This one is for the 50 volt version with let me think, with 2 amps rating. I will explain the details in the final video, where I also present to you some measurements of the real final filter. Same size and a same PCB, but this time with 100 volts capacitors. The other elements you might see remain the same, but the capacitors are rated and that way much bigger. Also rated for, no, in this case it's half amp, and that way we could use a bigger inductance here for the common mode choke. So this is the half amp 100 volt version. And finally the biggest one, same size of PCB but with a different layout, and this time the really big and heavy 400 volts capacitors, which take a substantial weight and height. And for all 3 versions we also provide such a protective cover, a shielding box out of solderable tin-plated sheet metal. And you can see we here have the tinned copper traces where this can be soldered to, so that you get as good as possible connection to the output ground. And so that's a short introduction to our final filter, and I hope you liked it. Perhaps if you could learn something, if it was interesting for you, then give it a big thumbs up, and see you for the final episode with some measurement and some detailed explanation of our new EMI filters, in 3 sizes and 2 different amps rating. So that was it for today. Thanks for watching. Bye from Roger. Bye from Kanka Labs.